Hi, this is Nageswara, Assistant Professor of Physics, Government Degree College, Chintalapudi. In this presentation, I want to analyze chromatic aberration. So before discussing about the chromatic aberration, so you want to explain what is aberration and how many types of aberrations are there, what is chromatic aberration, how many types of chromatic aberrations, and how can we calculate the magnitude of the chromatic aberration. So actually this is the convex lens. If a point object is placed in front of the convex lens, the image is formed at the another side. If the object is point object, the image is also required point image. If the image is also point image just like object, there is no problem. But in actual practice, due to the problems in convex lens preparation and due to the light used, the image is not a perfect object. This defect in lens is called aberration. So the aberration can be defined as the deviation from the actual size, shape, color, and position of an image of the object produced by a lens is called an aberration, or also called defect of a lens. For example, this is a convex lens. If this is the principal axis, if a point object is placed on the principal axis, left side of the convex lens, there is a two rays which is passing through the convex lens and images formed at IM and IP. So IM is nearer to the convex lens and IP is far from the convex lens. So for the single object, there is a two images we are observing here. And at the same time, the second diagram, there is a white object. So the white rays is incident on the convex lens and scattered into 7 colors. So there are 7 images are found. One is violet image AVBV and second one is red image ARBR. Remaining 5 color images are found in between AV and AR. So there is also perfect image is not fixed there. So this type of defects are called aberrations. Why these aberrations are happening? Aberrations are due to light used and also due to the optical system used. How many types of aberrations are there? There are two types of aberrations. One is chromatic aberration and the second one is monochromatic aberration. What is chromatic aberration? If the object light is not monochromatic, it is nothing but that is multicolored. If it is white light, then the image formed by the lens is colored and also at different positions and also uh, just and multicolored and also at different positions. This kind of aberration is called chromatic aberration. So if the light is not monochromatic, then the image becomes multicolored and the defect is known as chromatic aberration. There are two types of chromatic aberration. One is longitudinal chromatic aberration and the second one is lateral chromatic aberration. So what is monochromatic aberration? If the light is not multicolored, if it is light is monochromatic, that is nothing but single color. That is also called single wavelength. The image formed by the lens is not a perfect image, its a shape and a size may be changed. This type of defect is called monochromatic aberration. So if the light is monochromatic, several defects in shape and size are found. Such defects are known as monochromatic aberrations. So again, monochromatic aberrations are 5 types. One is spherical aberration, second one is coma, third one is astigmatism, and fourth one is distortion, and fifth one is curvature. What is how many types of chromatic aberrations are there? There are again two types of chromatic aberrations we have. One is longitudinal chromatic aberration, and the second one is lateral chromatic aberration. In longitudinal chromatic aberration, If the object is placed on the principal axis of white object, the white light is incident on the convex lens and scattered into different colors. Then the violet is formed nearer to the convex lens and red image far from the convex lens. Remaining five colors are formed in between IV and RV. This type of aberration is called longitudinal chromatic aberration. So, what is its magnitude? The magnitude is equal to the distance between two images, that is IR minus IV. So, the longitudinal chromatic aberration can be defined as the formation of images of different colors in different positions along the axis is known as longitudinal chromatic aberration, are also called axial chromatic aberration. And what about lateral chromatic aberration? We know when the light is white color, different color images are formed at different places. Not only that, its magnitudes are also different. So, the change or difference in magnitude of different color images is called lateral chromatic aberration. So, as seen in the diagram, AB is the white light. When light is incident on the convex lens, there is red image is formed at ARBR and violet image is formed AVBV. We know the size of the red image ARBR is greater than size of the violet image AVBV. The difference between those two images sizes is called lateral chromatic aberration. So this is the red image, this is the violet image. So the definition can be defined as the images of different colors are formed by different positions or different sizes due to the magnification of white object is different for different colors. This defect is called lateral chromatic aberration. So the lateral chromatic aberration is equal to ARBR minus AVBV. So how can we calculate the magnitude of the longitudinal chromatic aberration of a thin lens? So there is two cases. When the object is at infinite distance, that is the first case. When the object is at finite distance, that is the second case. In the first case, when the object is at infinite distance, how much is the quantity of longitudinal chromatic aberration? So in this diagram, that is the principal axis, that is the convex lens. If the object is at infinity, the rays coming from the object is parallel rays. These rays are passing through the convex lens and scattered into different colors because that is a multicolored light. If it is white light, violet image is formed at FV. Red image is formed at FR, where FV is the focal length of convex lens for violet color, FR is the focal length of the convex lens for a red color. So in this case, we know according to the definition, the longitudinal chromatic aberration is equal to FR minus FV to be calculated. So we know according to the lens formula or lens maker formula, if the focal length is f, 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2, where f is the focal length, mu is the refractive index of the material, r1 and r2 are radii of curvatures of the convex lens. If this equation is applicable to violet color as well as red color, then what happens? In case of violet and red colors, F is Fv, that's 1 by Fv is equal to mu V minus 1 into 1 by R1 minus 1 by R2, where Fv is the focal length of a convex lens for violet color, mu V is the refractive index of the material of the lens for a violet color. In case of a red color, the focal length equation can be written as 1 by Fr is equal to mu R minus 1 into 1 by R1 minus 1 by R2, where Fr is the focal length of the lens for red color and mu Vr is the refractive index of the material of the lens for a red color. From the above equations, when subtracting each other, 1 by Fv minus 1 by Fr is equal to mu V minus mu R into 1 by R1 minus 1 by R2. So when taking LCM both sides, then Fr minus Fv by Fr is equal to mu V minus mu R into 1 by R1 minus 1 by R2. If it is multiplied and divided by, if it is multiplied and divided by mu y minus 1, then this equation can be written as Fr minus Fv by Fr is equal to mu V minus mu R by mu y minus 1 into mu y minus 1 into 1 by R1 minus 1 by R2, where mu y is the refractive index of the glass material for yellow color, where yellow is color or may be written as mean color of the violet and red color. So then, so that can be written as Fr minus Fv by Fy square is equal to mu V minus mu R by mu y minus n into 1 by Fy. Why it is writing 1 by Fy is equal to, we know, mu minus mu y minus 1 into 1 by R1 minus 1 by R2. From that, 1 by R1 minus 1 by R2 can be written as 1 by Fy into mu y minus 1 into Fy. And Fy square, how it can be written as Fy square? We know Fy is the mean focal length of the violet and red color. So this can be written as Fy square is equal to Fv into Fr. So that's Fy into Fy square can be written as in place of Fy into Fr. So that is Fr minus Fv by Fy square is equal to mu V minus mu R by mu y minus 1 into 1 by Fy. But we know the dispersive power of the material omega is equal to mu V minus mu R by mu y minus 1. When substituted into this equation, that mu as Fr minus Fv by Fy square is equal to omega by Fy, where Fy is cancel each other, so that Fr minus Fv is equal to omega Fy. We know according to the definition, the longitudinal chromatic aberration for the object is at an infinite distance is equal to Fr minus Fv. So that Fr minus Fv is equal to omega Fi is the equation for longitudinal chromatic aberration. So the longitudinal chromatic aberration for a thin lens for an object at infinity is equal to the product of its mean focal length and the dispersive power of the lens. This is the longitudinal chromatic aberration for a convex lens when the object is at infinity. If the object is at finite distance, how can we calculate the longitudinal chromatic aberration? In which there is a principal axis, a convex lens is there. If the object is finite distance, that is AB is the object of white color. Then the white ray is incident on the convex lens and splits into different colors and formed violet image AVBV and red image ARBR. Now you know, according to the definition, the longitudinal chromatic aberration is equal to ARBR minus AVBV. How can we calculate? For a thin lens, we know the focal length equation is 1 by f is equal to 1 by v minus 1 by u, where f is the focal length, v is the image distance, and u is the object distance. So 1 by f is equal to 1 by v minus 1 by u is the formula for the focal length. From our school days also, we can listen number of times this equation. But in this, we have to calculate the distance between two images. The distance between two images, that is equal to AR minus AV, is the longitudinal chromatic aberration. So that is if the distance is for the red image is taken as VR, the distance of the violet image distance is VV, then the longitudinal chromatic aberration can be written as VR minus VV. This is called longitudinal chromatic aberration when the object is at finite distance. So for this case, we have to differentiate above equation, that is 1 by f is equal to 1 by v minus 1 by u. When differentiation both sides, we know differentiation of 1 by f is equal to minus df by f square, and differentiation of 1 by v is equal to minus dv by v square, and differentiation of 1 by u is equal to 0, because u is the object distance that is constant. So we know differentiation of the constant is 0. So we can write minus df by f square is equal to minus dv by v square. So that df by f square is equal to dv by v square. Or df is equal to difference in focal length of two colors, that is equal to fr minus fv. According to the previous equation, fr minus fv is equal to omega fy, and dv is equal to vr minus vv. When substitute these two equations into above equation, df, that is omega fy, by f square is equal to dv, that is vr minus vv by v square. But we know f is the mean focal length of red color and yellow color, red color and violet color. So f square can be written as is equal to fy square, and also v square is equal to vy square, that is for yellow color. So that omega by fy square is equal to vr minus vv by vy square. So the longitudinal chromatic aberration is vr minus vv is equal to omega by fy into vy square. So according to this, the longitudinal chromatic aberration when the object is at finite distance, depending on the dispersive power of the lens material and focal length, the average focal length, and also average distance. This is the value of longitudinal chromatic aberration. Thank you.